In this lecture, we're going to talk about what happens after the system is placed into production. So even though it's in production, you still have things to do. And one of them is you can possibly run some particular tests. So there's a concept of testing in production. And there are two different types of testing that can happen. One is where you actually put problems into the system and measure the response. That's called chaos engineering. We'll go into that in a minute. The other is a passive type of testing where you're not affecting the testing, and that is you have a scanner that looks for various types of problems and possibly perform remediation if there's a problem, or possibly just inform you. And again, we'll go into that. So let's talk about chaos engineering. Chaos engineering is essentially an experiment, and you want to ensure that your system has the ability to withstand what are called turbulent conditions in production, or possibly the staging environment. Turbulent in this sense means something went wrong. And it's about building trust and confidence in your system from introducing chaos in a variety of, again, controlled ways. So the reason for chaos engineering is that production systems have evolved beyond the human ability to mentally model the system. And this is because the speed and the scale and the complexity of modern software is challenging behavior. This is a picture of the interconnections of a Netflix system. Netflix has somewhere in the order of 1,000 microservices. Netflix may have as many as 10,000 or 100,000 users simultaneously. This is not something you can test before you put it into production. So the idea behind chaos engineering is that you build a hypothesis about what you would like the steady state behavior to be. And you focus on something that is a measurable output of the system. And then you introduce potential real world events, and you prioritize the events by their potential impact or their estimated frequency in order to choose which event to do. And you run an experiment in production. So systems behave differently depending on the environment and the traffic patterns. You want to automate the experiments to run continuously, although not too continuously, so to run periodically. And you would build automation into the system to drive both the orchestration and the analysis of these experiments. Blast radius is a term that says what is the potential impact of introducing a problem, and you want to minimize that. And so you want to ensure that the fallout from experiments are minimized and contained. So you do the experiment while the system is running, but you don't want to impact users in any negative way. So you start by defining a hypothesis, and you brainstorm. What can go wrong? What if the database is down? What if the service responds slowly? What if the service iPod? What if a container dies? What if a load balancer stops? What if an autoscaler is unable to create a new resource? What happens if the cloud policy changes? You brainstorm all of the kinds of things that can go wrong, and you use that to structure your experiment. And there are a set of tools that are involved in this, or at least potentially. So one is called Chaos Monkey, and that's a tool that randomly kills executing processes. The orchestrator is involved, and so that would manage your MySQL replication. So MySQL is a database system. There might be a monkey that involves Kubernetes. So this is a implementation of the Chaos Monkey for Kubernetes clusters. There's something called Gremlin, which is failure as a service. So you might have your cloud provider actually introduce problems. And there's a toolkit. So there's a chaos engineering toolkit that would help you build confidence in your system. Some more, there's something called SteadyBit, and that's a platform, cloud platform that has auto discovery features, different attack types, different user management, and many more. So you would use it for security. There's something called Powerful Seat that adds chaos, again, a Kubernetes test. There's something called Drax, which helps you test against various types of deployment, and it's inspired by Chaos Monkey. So there's a whole collection of tools. Um, the way to manage it is best exemplified by what Slack calls their disaster place theater. So Slack is a communication tool that is widely used in DevOps and other things to enable teams to communicate. And they have what they call the disaster piece theater, and it's very structured. So first of all, they define what the exercise is. So the exercise might be, we're going to test one of these things that we brainstorm. And it takes place at a well-publicized time, well-publicized within Slack. And they make sure that the relevant experts are either on the same room or in constant communication through video. And then someone writes a detailed plan of what's going to happen, and they publicize it again within the company. And the plan is a detailed collection of activities, including what fault will be introduced and what should be monitored. And it establishes a specific hypothesis that is going to be tested. So in the Netflix context, the hypothesis is that we have some relatively constant number of new videos within a time frame that people are starting, and we don't want that to change. So that's what we're going to measure. In Slack's case, they depending on what the problem is, they define what's going to be measured. So it's all very well scripted, very well publicized. Everybody in the company knows what's going to happen. The experts are available, and then they introduce the problem. And they look at the logs and so on to verify that the expected results appear. So they verify that they occur. First, they do it in a dev environment to make sure that they have their scripts for introducing the problem correct, make sure that the experts see the results that they expect in the development environment. And then they introduce the failure in production and they monitor it. And then they do an analysis. What was the time to detect and time to resolve? So this was a real problem. It may have produced, we'll talk about incidents later in this lecture, but it may have produced an incident. How long did it take to find the problem? How long did it take to resolve it? Was this something that users would notice? And the goal, of course, is that you don't want users to notice. Did it require human intervention? What was scary about this particular thing to the people involved? Was any of the documentation about what to do incorrect? Because it may be that when a problem occurs, somebody will look up the problem in a set of documentation, and it'll talk about what the remediation is, and it's possible that that's incorrect. Were any of the dashboards in Grafana, that's their dashboard, their monitoring system, out of date? So that is the debrief. And that takes care of how they do it. The debrief will have found if everything works, they're perfectly happy. If there was something they discovered that went wrong, it would get on the list to get fixed. The other type of testing in production is an environment scanning. So this is not disruptive. This is a passive type of thing. It's not going to affect any users. So compare it to chaos engineering, it's much less it's extremely unlikely to cause a problem. And a scanning tool looks at your environment, and it looks for different kinds of problems. We talked about infrastructure drift early. Does it find infrastructure drift? Are there incorrect security settings in any of your processes? Are there machines that are not being used? Okay, have you created a virtual machine and it is idle? Well, that indicates a problem. If nothing else, the virtual machine should be deleted, but then why is it idle? Uh, and these scanning tools will go through your environment, look for a collection of different, has a vulnerability occurred in any of the pieces of software that you've included in your system. And the SBOM, which we talked about, is a useful tool for that. So they look at the SBOM, they compare it to the list of known vulnerabilities, and they say, are there known vulnerabilities in anything that we're running, because a vulnerability could have been introduced over time, could have been found over time, uh, and may not have been found initially. And so a scanning tool takes CPU, takes memory, takes disk, takes network access, but it doesn't perturb the running system. And so there are a variety of different scanning tools. There are conformity scanners that check if instances are coded to best practices and shuts them down. And what happens when it finds something is it sends a nasty email to the owner of that system. So when we of that service. So when we talked about microservices, we said every microservice is owned by a particular team. And so if you find a problem in a microservice, then you inform the team that owns that, and then it's their responsibility to go ahead and fix it. There are security scanners, so they look for security weaknesses. Have all the settings been set correctly? Are the IAM settings correct? Again, has a vulnerability been discovered in one of the pieces of software that you used? And they look at your certificates. Is it, are you about to have an expiration of some kind of certificate or some kind of license? Okay, that could shut down the system. So they look for those types of things as well. Uh, there are things that look for health. I talked about finding virtual machines that are not running or containers that are not running. And the janitor looks for, again, unused resources and discards them. So questions to discuss. How does a janitor scanner work? How does it know all of the resources that are associated with your account? How does it detect that there's a problem? And how does a security scanner work? Again, I gave you a hint when I talked about the SBOM. Okay, now let's move on to the notion of service level agreements, and there are three different types of service level thresholds. So a service level agreement is an agreement between a service and its clients and identifies a metric. So what is the request latency that I will guarantee, that I as a service will guarantee that you get, okay, with a certain level of requests. So if you send me 100 requests per second, then I guarantee that I will respond within 10 milliseconds, let's say. And so the agreement has a threshold. So 99% of the requests receive a response within 300 milliseconds is the example I'm using. And a typical agreement will contain many of these thresholds. Sometimes they're with internal clients, sometimes they're with external clients. If there are with external clients, then these SLAs may be part of a legal contract. And so it becomes very important that your system manages them. You do not want to be informed after a service level agreement has been breached. You want to be informed that there is a potential that you will breach the service level agreement. And so that's where service level objectives come in. So you set something that is more stringent than the service level agreement, and you say, notify me if this service level objective is violated. And so this gives you a chance. So it generates an alert. It gives you a chance to fix the problem before you violate your service level agreement. Some types of service level agreements are not easy to measure. So, for example, if I give you an availability requirement, it's going to have 4 nines, 99.9999% of the time it's going to be up over some period. You don't really know if you violated it until that period has passed, or if you're about to violate it until that period has passed. And so you can't really test it. And so the notion of having a service level objective doesn't mean anything for that. If it were a latency requirement, then that's a different story. But for some things, it's difficult to measure that, and that's where a service level indicator comes in. So a service level indicator is a proxy for the service level objective. So, for example, for availability, you might talk about how many requests are not satisfied. And that would be your indicator, your SLI. And so the SLI is what you're actually going to measure. Again, in terms of latency, you can measure latency. In terms of availability, you need to have some sort of proxy. And so the SLIs are monitored on some basis. The period will depend on the maturity of your system. If you just put a new service into production, then you want to monitor it more closely than one that's been running successfully for the last 2 months or so. And the service has to have instrumentation that exposes the thing that you're measuring. So one of the tenets of software engineering is you keep things hidden. You don't want to expose things because they might be affected by external things. And so you have interfaces as a way of blocking what clients can see from a service and so on. Okay, well, this is an example where that isn't appropriate. You want to expose something. So if you think about when you're downloading a piece of software, you see a progress bar. Okay, well, that's the actual measurement of the process is buried in the guts of the thing that is doing the downloading, and so you need to be able to you need to export that so that it can in fact be displayed. So typical SOI, latency and throughput. I talked about request satisfaction is a surrogate for availability. Traffic, how many requests do you have? How many I/O requests are you making? Again, you may have designed your system to handle a certain number of requests. If it goes over that, then you may want to adjust your auto scaling rules. But in the meantime, you may have to, well, it wouldn't be manually, but you may have to automatically create a new instance outside of the auto scaling process because the traffic is too high. Saturation, that's a different measure of traffic. Traffic is an event. Saturation is a percentage. So if your disk is 90% full, that indicates a problem. If your network traffic is at a sufficiently high percentage, that indicates a problem. So that's another SLI type of thing. So things to discuss. What is the quality in addition to availability that could not be directly measured? What's an SLI for that quality? What does an availability of 99.99% actually mean in practice? And then finally, let's talk about incidents. So an incident is an event that could lead to loss or disruption of an organization's operations. Something has gone wrong. In software terms, an incident with a running system is either a performance or an availability problem. Security incidents are dealt with by security specialists, and that's outside of our discussion here, but they may be a portion of a response team. So what's the life cycle of an incident? An incident is detected by a monitoring system based on threshold values that you've established. So you have to set up a set of rules saying that if utilization of a processor is more than 80% for a sufficiently long period of time, then that requires an alert and requires attention from somebody. So the monitoring system then sends out a page to the first responder. So we'll talk about first responders in a minute, but that historically was the operator and now is shifted to other classes of employees, and we'll talk about that. The monitoring system also enters the incident in an incident repository. So back in the beginning, we talked about there being a tremendous number of repositories and databases that DevOps practices use or create or enter data into, and this would be one of them. So the incident repository is frequently called a ticketing system, and that's historical. It used to be that you would create a ticket, which may have been a piece of paper. I mean, we're talking prehistory now. May have been a piece of paper, and that ticket is passed around until somebody finally resolves it. And we talked about incident. We talked about things like Jira, which was a tool that you use to log activities. Okay, and so one activity might be that there's an incident outstanding. And so there are two goals when an incident occurs. The immediate goal is to fix the production problem, the current problem, get the system running normally again. So if it's a problem with utilization of a CPU, create another instance. If it's a problem with the disk, then move the files off the disk and shut the disk down, and then work normally again. The second goal is to determine what was the cause. If the root cause was a software problem, then you need to fix it. If the root cause is a hardware problem, then you need to inform the operations team who will replace the hardware, swap out the hardware. And so you don't want it to happen again. The first responder, and it may be that the first responder can't figure out the problem and they need help. So they have a list of people to call in particular circumstances. The first responder diagnoses the cause of the incident and determines the workaround. Satisfies the first goal. Once the system is running normally, then this ticket goes to a team, and the team includes the first responder, probably, and members of the development team, and they do a root cause analysis and decide what needs to change, if anything, either in the code or in the process. It may be that the process, we need to add a new test. It may be that we need to do more peer reviews. So it could be there's a code problem. It could be that a problem stuck through the pipeline. And so the root cause may be a process cause. And so then that process needs to be modified somehow. And so this is what happens after the incident is fixed. So the first responder, again, in conjunction with the development team, determines the root cause. And you enter this into the ticketing system, and then the development team can act on this or not, depending on what other priorities they have. So there are three different models for dealing with incidents. There is one called You Build It, You Run It, which is due to Amazon. There is one that involves a special team called Site Reliability Engineers, and that's due to Google and is being fairly widely adopted. And there's something called Production Engineering, which is due to Facebook. So You Build It, You Run It there's a quote here that you can read on the slides. And basically it says you're a developer, you understand what went wrong, so you can fix it. And more than that, you get some feedback, immediate feedback into what went wrong. And that's the Amazon philosophy. The developers are responsible for the post-production. So if you're a developer in Amazon, you wear a pager or you have a special device that responds to pages quickly. And the first responder and become the first responder. Now, someone is not the first responder 24/7. Somebody, that you rotate that among the developers. And so, you may be on call if there's a problem, 6 hours or 10 hours a day, or however the rotation is defined. Uh, the assumption behind the Amazon model is that the developer is familiar with the internals of the system that's failing. And that's certainly true, but it may be that the cause for the failure is something external to the particular service. Maybe it's a downstream service that isn't responding quickly enough. It's getting overloaded. Maybe it's a network problem. And so the assumption behind the Amazon model is not necessarily true. It could be true in some set of cases, but not necessarily in all the cases. And so the drawbacks are it assumes that because the service triggered a norm, the service has a problem, again, as I said. But the problem may be in the network. And the assumption is that the developer has a good understanding of all of the contextual elements of a particular service. The second philosophy is the site reliability engineer. And so Google, Netflix, and this is being fairly widely adopted, creates an organizational unit called a site reliability engineer. And a system is assigned to an SRE team. And a member of the team will be the first responder, again, when an incident occurred. And again, the duty is rotated among members of the team. So the site reliability engineer assumes that the SREs have an overall understanding of the system and environment. They may not have the deep understanding of a particular service, but they do have an understanding of the overall system. And the SREs will monitor the SLIs, and they'll share a knowledge base of problems with other SREs, so that as an organizational unit, they have a broad perspective in terms of all the different things that are going on, and they have a knowledge base and they share with other SREs. It's possible that the development team doesn't listen to the SRE. I know some people who have been SREs, and that was one of the complaints I heard. And so the SRE team has the option of saying to a development team, we're not going to support you. We told you what was wrong. You didn't fix it. It kept coming up. We're not going to support you anymore. You now become the first responder. And so this is the stick that the SRE team has to make sure that the developers listen to their advice. And then the final model is production engineering, which is kind of right in the middle of those. So this is production engineer is responsible for reliability. They are embedded within a development team. So they understand a particular development team, but because they have the skill set and the knowledge to understand how the system works. So it's sort of half, you build it, you half run it, and half SREs. So suppose you're a developer. What's your reaction to wearing a pager? Why would a development team not act on the recommendations of the first responder? Those are things to discuss offline. And that's the end of this particular chapter.